All right, welcome back to the deep dive. So I have to start today with this paradox. It's something that honestly kept me up last night after I was reading through the research stack you sent over. We spend so much time talking about AI as this godlike cumulative force. We see the headlines about it, crushing grandmasters at Go, writing poetry, diagnosing diseases better than specialists. You think it's just this unstoppable line going up.
It certainly feels that way from the outside. Yeah, a straight trajectory.
Exactly. But here's the paradox. That same AI, the one that can write a sonnet, it massively struggles with something every single human toddler does naturally. It fails at the most basic aspect of growing up.
And what's the specific toddler skill you're thinking of?
Learning a new skill without completely erasing the old one. It's like we've built these geniuses that have the memory of a goldfish when you ask them to learn two things in a row. So today we were diving into continuous learning, lifelong learning in AI.
This is one of my favorite topics because it really is the holy grail of AI research. We're not just talking about making AI faster. We're talking about fixing a really fundamental structural flaw in how these things are built. We have a great stack of papers today, too, from the foundational stuff in the late 80s all the way to cutting-edge work from DeepMind and OpenAI.
So our mission for this deep dive is to figure out, why is this so hard? Why are the smartest machines on Earth so brittle? We're going to look at the specific hurdles, and then this is the part I love, the bio-inspired solutions. They're basically looking at our brains and trying to steal the cheat codes.
That's a very accurate way to put it.
Yeah.
It's a bit of reverse engineering our own biology to patch the machine's code.
Okay, let's unpack the machine side first. What is actually going on inside that neural network? Why can't it just remember?
To get that, we have to define the core problem. And in the field, it has this very dramatic, almost cinematic name, catastrophic forgetting.
That sounds like a heavy metal band or a really bad exam result.
It does. But it's a real technical term. It was formally described by researchers McCloskey and Cohen way back in 1989. So it's not a new problem, but it's gotten much more urgent as AI has scaled up. And it was ratified and explored much deeper in a 2017 study by Kirkpatrick.
So what's the technical reality behind that scary name? Because when we learn, we just add information. Why does the AI subtract it?
So here are the simplified mechanics. A neural network learns by adjusting weights. Think of them as millions of tiny knobs tuning the signals. When it learns a task, like recognizing a dog, it tunes all those knobs to the perfect state for dog.
Okay, so the knobs are all set to dog mode.
Right. But here's the catch. When you show that same network a new data set, let's say cats, and you tell it to learn that, it doesn't use the leftover knobs. It aggressively retunes the same knobs to optimize for cat. It literally overwrites the mathematical values that encoded the dog. It's not malicious. It's just trying to minimize error on the current task. It assumes the old one doesn't matter anymore.
So it's not just that it gets a little rusty on the old topic, it's a total system wipe.
Precisely. The efficiency with which AI forgets is kind of alarming compared to our brains. It doesn't fade, it's overwritten. The whole geometry of the network shifts.
I found an analogy in the notes that I think just makes this so clear. Imagine your brain worked like a current AI. You decide, okay, I want to learn how to brew the perfect cup of coffee. You practice, you get it right, and the moment you master it, your brain automatically resets the part that knows how to tie your shoelaces.
That is the reality for these models.
So you're just standing there with your perfect coffee, but you can't walk out the door because you have no idea how to tie your shoes. And if you relearn how to tie them, poof, you forget how to make the coffee. You'd be stuck in this loop just swapping one skill for another.
That is exactly what happens. And for a long, long time, the only way to fix this was to retrain the system on everything from scratch every time. You'd have to show it the dogs and the cats all over again, together, in one massive batch.
Which sounds incredibly inefficient. I mean, we don't do that. I don't have to reread every book I've ever owned just to learn a new recipe.
No, because that would be energetically impossible for us. And that brings us to the solutions. Since we don't suffer from this, scientists are looking directly at the brain's biological mechanisms. We've basically identified 4 main strategies that are leading the research right now.
Let's break these down. So, strategy 1. This one felt the most intuitive to me, but also the weirdest. It's called replay, or recapitulation.
Yes, this is based on a 2017 paper by Shin and his colleagues on something called generative replay. And the intuition here comes directly from how you and I sleep.
Sleep. I thought we were talking about active learning.
We are, but think about what your brain does when you sleep. It doesn't just shut off. It enters a consolidation phase. It literally replays the day's events, firing those same neurons again to strengthen the connections. That's how things move to long-term memory. Generative replay tries to mimic this dreaming process inside the machine.
But an AI doesn't sleep, so
Yeah,
how does it...
it's fascinating. The architecture uses a two-part system. There's the solver, which is the worker bee doing the new task, and then there's a generator. The generator's whole job is to create synthetic data that looks like the old tasks.
Synthetic data, so it's just making stuff up, fake data.
Yes, it essentially hallucinates examples of the previous task. So while the AI is training on a new task, like recognizing cars, the generator is simultaneously creating fake images of the old task, like horses, and mixing them into the training stream.
I see. So it's tricking the network. It's saying, here are the new cars, but hey, here are also some fake horses so you don't forget what they look like.
Exactly. And it doesn't need to store the original horse photos, which saves a huge amount of memory. It just needs a generator that knows the concept of a horse.
It's like, if I'm cramming for a history exam, but while I'm studying, I force myself to review my old biology notes so I don't lose that foundational knowledge.
That's a great comparison. You're artificially keeping the old memories alive. It anchors the weights using these self-generated memories.
Okay, so that's replay. Dreaming to remember. Strategy number 2 seems more structural. Synaptic consolidation. This one sounded like it involved a lot more math.
It does, but the concept is beautiful. This comes from that seminal 2017 paper I mentioned by Kirkpatrick called Elastic Weight Consolidation, or EWC.
Elastic weight consolidation. Okay, let's decode that. Elastic sounds like it can stretch, but consolidation means it stays put. That feels like a contradiction.
It's a balance. Here's the logic. In our brains, not all synapses are equal. Some are very plastic. They change easily. That's for, a phone number you only need once. But others, the ones holding core skills or long-term memories, are much more rigid. They don't change easily. EWC tries to do the same thing with math.
So the algorithm looks at its own network and says, okay, this specific connection here is really important for remembering what a dog is. Do not touch it.
Effectively, yes. It uses a tool called the Fisher Information Matrix.
Whoa, okay, fancy name. What does that actually do?
Don't worry about the math. Just think of it as an importance map. After it learns a task, it runs a diagnostic and identifies which artificial synapses were crucial. Then, when it learns a new task, it makes those specific connections expensive to modify.
You mean computationally?
In computational terms, yeah. It adds a penalty and error cost to changing them. So the network naturally tries to learn the new task using other connections, the ones that aren't marked as important, leaving the crucial old ones alone.
I like the idea of a soft lock. It's like putting a do not disturb sign on certain memories. You tell the construction crew, renovate the building, but you are absolutely forbidden from touching these load-bearing walls.
That is a perfect way to visualize it. It allows for plasticity where it's needed, but stability where it's critical. It balances the two, just like our brains do. If you change those walls, the old knowledge collapses.
Okay, on to strategy number 3, dynamic architectures. This one feels a little bit like cheating, but in a really clever way.
It is a bit of a brute force solution compared to the others, but it's very effective. This comes from the Progressive Neural Networks paper by Rusu and colleagues.
This is where we stop trying to cram everything into one box.
Correct. Instead of forcing one fixed network to learn everything, the system just creates new modules, new columns of neurons for every new task.
So if I learn to play tennis, I literally grow a new piece of my brain for it.
Essentially. And here's the trick. These new columns are connected laterally to the old ones. So the new tennis column can look at the running column and say, hey, I can borrow some of that knowledge about moving my legs,
Yeah.
but it won't actually change the running column.
It's like instead of formatting my hard drive every time I install a program,
You just plug in an external one.
I just plug in a new external hard drive. I keep adding storage for every new skill.
Yes. But what's the obvious problem with buying a new hard drive every week?
Well, eventually my desk is just full of hard drives. The
Yeah.
system gets enormous.
Exactly. That's the scalability issue. If an AI lives for 20 years, does it become impossibly massive? It guarantees you don't forget,
Right.
but the computational cost grows and grows. It's a trade-off.
Right, which brings us to the last one. Strategy 4, meta-learning. This one sounds the most futuristic to me.
It's often called learning to learn. A key paper here is by Finn and others from 2017 on few-shot learning.
This is about giving the AI a manual on how to study, isn't it?
Yes. Instead of just feeding it raw data and saying figure it out, we're trying to train the model itself to be adaptable. We want an AI that sees a new task and thinks, I know how to learn this quickly with minimal interference.
So rather than memorizing the answers, it's learning the method of studying.
Precisely. It's about optimizing the network's initial state so that it's just ready to adapt to anything. It's a higher level cognitive strategy. Less about what it learns, more about how it learns.
It's fascinating because every single one of these strategies, replay, consolidation, dynamic growth, they all point back to us, to biology. It feels like we're just running in circles trying to recreate what nature already figured out.
And that's the mirror aspect of all this research. It's a two-way street. We use AI to try and understand the brain, and we use the brain to improve AI.
You mentioned some specific biological mechanisms, like we actually have chemicals that do what that EWC algorithm does.
We do. It's called neuromodulation. Chemicals like dopamine and acetylcholine act as signals in our brain that essentially mark memories as important.
So when something emotional or significant happens, dopamine hits that synapse and says, lock this in.
Exactly. It tells the synapse, this just mattered, solidify this connection. That is biological weight consolidation. The EWC algorithm is just a mathematical translation of what dopamine does. We're writing code that mimics a chemical reaction.
That is just wild. We are reverse engineering the chemistry of our own memories into pure math.
And there's a great quote I want to share from Jan LeCun, one of the godfathers of deep learning. He said, unsupervised learning is the dark matter of intelligence.
Okay, unpack that. Dark matter.
He's saying the bulk of what makes us smart is hidden. It's the background learning we do just by observing the world. But if that's the dark matter, a lot of researchers now believe that continuous learning is the dark energy.
The force that's driving the expansion of the universe.
Or, in this case, the expansion of the mind. It's the force that allows intelligence to actually grow over time without collapsing. It's what turns a static database into an evolving mind. Without it, you have an archive. With it, you have a being.
So let's pivot to the so what. Why should you, the listener, care if a robot can remember how to make coffee and tie its shoes? What does this change in the real world?
No, the implications are massive. Let's start with robotics. A home robot today is programmed for a fixed set of tasks. If you wanted to learn a new recipe, you run the risk of it forgetting a core safety protocol.
Right. I don't want my robot to learn how to make a perfect souffle, but forget that it's not supposed to drop a hot pan on my foot.
Exactly. Safety and reliability in dynamic environments depend on this. You need a robot that adds souffle to its repertoire without deleting "don't stab the human."
A very important baseline feature, yes.
Then there's personalized medicine. Imagine a diagnostic AI that learns the specific nuances of a new patient population, maybe a certain genetic trait in a region, without unlearning general medical knowledge from millions of other cases.
That's huge. It becomes a specialist without ceasing to be a generalist. It builds on experience instead of replacing it.
And there's one more implication that's surprisingly environmental: sustainability.
Ah, the carbon footprint of AI.
Yes. Training these huge models takes an enormous amount of energy. Server farms running for weeks, consuming gigawatts of power.
And right now, if they want to update a model, they often have to retrain huge chunks of it from scratch, right?
Often from near scratch. It's like building a new skyscraper every time you want to add a floor. If you solve this, we can just top up the model with new info. It would save massive amounts of energy.
That's a great point. It makes AI greener. But, and there's always a but. We're not there yet, are we? The sources were very clear this is still an active struggle.
No, not at all. Most of the success we've seen works well in, controlled lab environments, on specific data sets like Atari games. The real world is much, much messier.
One of the challenges was scalability. We touched on this with the dynamic architectures. But even with the other methods, does the brain eventually just get full?
That's a major hurdle. How do you manage a system after decades of learning? Does it get too slow, too complex? And we also don't really have a standardized way to measure long-term learning yet. It's hard to test if an AI remembers something from 3 years ago.
And then there are the really provocative questions, the stuff that keeps philosophers up at night. The notes mention alignment.
Alignment is the big one. If a system is constantly evolving on its own without a human engineer pushing train, how do we ensure it stays aligned with human values? Who's responsible for what it learns on the job?
It's the bad influence problem. If my AI assistant spends too much time in the wrong corners of the internet, does it pick up bad habits the developers never intended?
It could. If it learns continuously, it's shaped by its experience, not just its code. It becomes a product of its environment. And that leads to this idea of identity.
The digital biography. That really struck me.
Think about it. If two AIs start with the exact same code, clones, but one spends 5 years helping a doctor in rural India and the other spends 5 years with a stockbroker in New York.
They're going to be radically different.
They will have learned completely different things. They'll have effectively different minds because of their unique learning history. Their response to the same question would be totally different.
So does that mean they have a unique identity? Do we have to protect that history? It's almost like if you reset that model, you're not just deleting software, you're erasing a unique perspective.
It definitely raises the question, is this the beginning of an artificial identity? Because for us, identity is just the sum of our memories. If a machine has a unique history of learning, does it have a unique self?
Wow, that is heavy. It shifts the whole conversation from software updates to personal growth.
So to summarize, solving continuous learning is really the bridge between the narrow AI we have today, these tools that do one thing well, and something like AGI, artificial general intelligence. It's the shift from static tools to robust, evolving intelligences. It's what will let machines actually live in our world, not just process it.
It's the difference between a calculator and a colleague.
Well put.
Before we sign off, I just want to leave you with a final thought from the research. The next time you walk into a room and completely forget why you went in there, or you can't find your keys, you would be grateful.
And why is that?
Because your brain might have those minor lapses, but at least it doesn't suffer from a total system wipe just because you learned a new lasagna recipe. You have this beautiful, messy balance of plasticity and stability that the smartest people in the world are desperately trying to copy.
We truly are walking marvels of biological engineering.
That we are. Thanks for diving deep with us today.
Always a pleasure.
Keep learning, everyone, and try not to overrate anything important. We'll catch you next time.